Welcome to the PTCS heat pump sizing class. Heat pump sizing in the PTCS program is critical to the energy savings and also to increasing year-round comfort for your customers. The benefits of the HVAC design process should be clear. Yes, we do want energy efficiency, and that's what PTCS is primarily about. But if we do size the equipment right and design the whole system, including the duct system correctly, we get greater comfort. We'll get less cycling on the equipment, which makes it easier on the compressor. We'll get lower auxiliary heat use, which is primarily where the energy savings from PTCS come from. And if we do everything right and make everybody comfortable and their bills go down, we'll get more customer compliments and fewer customer complaints. I know there's lots of rules of thumb out there. 1 ton per 400 square feet has been around for a long time. If that was ever correct, it was probably for a largely uninsulated house with single pane windows. So if it was ever correct, it's probably not correct today in modern homes with insulation and higher degree of air tightness. The 1 CFM per square foot of house, I know that's out there. Tonnage, this is my favorite, half the number of cylinders in the customer's biggest car or truck. What's in the shop today, and of course, keeping up with the Joneses, half-ton bigger than the neighbors. And of course, we have other ones such as this nice little cutout over here where you stand across the street on the curb and see how big the house takes up. The heat loss, heat gain analysis, the math is really pretty simple on it, and it's part of the ACA process. Manual J, which stands for Joule, is the heat loss and heat gain calculation. Manual S is once you get that heat gain and heat loss calculation completed, what's the best piece of equipment to put in that house. And Manual D stands for duct design. If you've never taken a duct design class, I urge you to do so. Getting the airflow right is critical to efficiency and capacity. So what are the penalties if you don't do things right? So if you're going to size right, you absolutely have to install right. And one of the biggest problems in heat pumps, as we all know, and air conditioners, is low airflow. This chart right here, if we start over here at 0 deviation from full airflow, basically we're saying we're getting 100% of the capacity. As we get down, say 20% low, we only have 90% of the capacity and 90% of the efficiency. And as we go down, we see that both the capacity and efficiency decreases as the airflow decreases. If you sold somebody, say, a 14 SEER air conditioner or a 10 HPF heat pump, if you do not have the correct airflow, they're not going to hit that goal. So once again, to size right, you have to install right. I know you probably all have the Hall of Shame photos from your competitors' shops that they installed. Manual J heating loads, it's really pretty simple on the heating side. It's that old Greek formula, if you will. It's UA delta T, or the U value, times the area of the basics of the building's components times the delta T. So basically what you do is you get the square footage, you look at the YAR and the U values. You get a duct multiplier, and duct multipliers, even if you do a duct leak test, is an estimate. If you don't do one, it's an educated guess. Air changes per hour, homes have certainly got a lot tighter. And when you're doing that, for any kind of furnace, you end up with, 4 or 5 basic choices. Manual J cooling loads, they get a little more complicated. One, again, you need the square footage and the U values. On windows, orientation is critical, shading, solar heat gain coefficient. The modern window lets so much less solar radiation through than it did, say, even 15 years ago. Duct multipliers, again, all of you on the webinar today have probably been in hot attics, and we put ducts up there, and the ductwork might have 65-degree air in it, and the ductwork might be in an environment where the attic's 135 degrees. That's a pretty big delta T. So yes, you're going to hear us, talk about the importance of at least looking at the duct system today. The internal gains, that's all the humans and the stuff that they plug into the wall and the narrow range. And you notice we have a lot more choices when it comes to heat pumps. They come in half-ton increments, which makes the need for precision a little higher. A word about duct multipliers. Yeah, this is kind of a funny picture. It's obviously a test house with a return running outside. But if you think about it, that's probably a more hospitable environment than the attic on this hot day, having it in the front yard. Typically, it's between 5 and 10%, and the duct multiplier is the penalty anytime you put the ductwork outside the house, either in the attic or the crawl space, sometimes the garage. 10% is about as good as you can get. That's well insulated and that's almost airtight. 20% sort of normal. And if it's 30% or higher, you really should consider fixing the duct system. It's hard to make people comfortable with a bad duct system that delivers warmer air than expected in the summer and cooler air than expected in the winter. So we hear a lot, so why can't we just sort of size by square foot? And really, more than square footage, it's the R value that matters. Over here, we can say basically this is the square feet of attic at various R values needed to create 1 ton of heating load. That's 12,000 BTUs per hour in Boise, Idaho. Boy, if you had an R0 attic, it would only take 500 square feet to create that 12,000 BTUs or 1 ton of load. By the time you get to R19, a big difference, you'd need 4,000. But at today's homes, with almost, a lot of homes out there having an R38 or higher, it takes 7,500 square feet. So what's more important than the size of the house is the R value, the U value, the heat loss, heat gain. This is another way of looking at the same information, if you will. This is BTUs through a 2,000 square foot attic with various R values. Again, we're in Boise again. At R0, oh my gosh, 42,000. That's a gas furnace all by itself. By the time we get down to R7, we get a big jump down, and R38, boy, we're much lower. This is not to say that high R values aren't important. Why not stop at R11? This is to say when it comes to sizing of equipment, the biggest differences come when you make a low R value higher. Let's get some definitions out of the way. Design temperature is not the coldest day of the year or the hottest day of the year. Usually the coldest day of the year happens at 2 or 3 in the morning. Chances are the house has enough thermal mass, if you will, it's already heated up, that it can ride through those few cold hours. If we size equipment for the hottest or coldest day of the year, we would probably have 2 systems in every house, and everything would cycle and lots of comfort complaints. Winter design condition, it means it only gets colder than 1 or 2.5% of the time, depending on what number you tend to use. In Boise, the average coldest temperature is -2. This is also called the mean extreme. However, the winter design condition is 9. In summer, let's be honest, your customers, what do they care most about? I want it cool, and I want it cool now. Portland is sort of the opposite. Our winter design temperature is 23, and the summer design temperature is 86. This 86 degrees, well, that is a very common summertime temperature. It's typically not the reason people buy air conditioners in Portland. They want to be able to cool their house when it gets, 90, 95, or even on the rare day, 100. So we're going to talk about the mean extreme a little bit later on today. Definitions, heating and cooling load. The heating or cooling load of the house is how many BTUs per hour, just like how the equipment is rated. The house requires to maintain the required indoor temperature at design conditions. Typical homes have heat loss rates of between 20,000 BTUs an hour and 80,000. Cooling loads typically range between 12 and 40,000. Equipment sizing. Relax, don't panic. There's sort of this old adage in the HVAC industry that close counts in horseshoes, hand grenades, and heat loss. This is not to say go out and guess, but the difference between an R38 and an R42 or an R33, this won't make much difference. The main thing is, get close. Get close, and it works. Most of the time we get to relax. What's meant by equipment sizing? What the customer wants. To be warm in winter, to be cool in summer. Pretty simple. They called you out there for a reason. When equipment sizing is really important. Furnaces, they have to be big enough to heat the house. Modern furnaces do not have much of a penalty for oversizing. People like to heat their house up in a hurry. That's why many contractors and consumers like 2-stage pieces of furnaces. Keep it within a nick size and everything will be fine. relax a little bit. Air conditioning. We are really fortunate. We live west of the Rockies. When we get hot days, we have low relative humidity. If you ever think you're having a humid day west of the Cascades, I really recommend that you get in your car, drive to the airport, and drive to New Orleans, where you'll really realize what mugginess happens to be. Heat pumps. Heat pumps are a little more tricky to size. They have to be big enough to heat the house down to 30. That's our recommended balance point. It's time to sweat the details a little bit. Getting the right size is crucial to saving energy and making the occupants comfortable. It's probably not panic time, but the level of detail needed to size heat pump equipment is a little higher. On furnace sizing, it's really pretty simple. You calculate the heat loss at winter design conditions. Size the furnace not to exceed 140%. That's ACA's guideline. In the average new house, the heat loss is about 20,000 BTUs. The smallest furnace you can buy really is 40,000. So you're already twice oversized, and I don't hear too many complaints because of that. Obviously, we can get absurd and start putting 100K furnaces in homes with 20K worth of load, and you're going to have comfort complaints and probably some equipment problems also. And yeah, PTCS realizes that sometimes you just need to put a larger fan in the air handler to handle the air conditioner sometimes. So furnace sizing, it's really sort of easy. It's really simple. You just sort of get the capacity tables out with. This one here is for a two-stage piece of equipment. It tells you the input at 40K on high, 26K on low. The output, this is obviously a high efficiency furnace, is 38 and 25. And again, we size on the output of furnaces, not the input. So real quickly here, what would be the right size unit for a house with 36,000 BTU hours worth of heat loss? There's not a big difference in cost in furnaces, so upsizing doesn't cost the customer too much money. But if we had 36K here, we see this 45K furnace here. The output's 36, so we'd probably say, I don't know if I want to be on the edge here. I think going up one size would be perfectly acceptable. What makes difference in sizing between heat pumps and furnaces? Well, the big thing about furnaces, they maintain their output regardless of the outdoor temperature. When it's 50 degrees outside, they have the same output as when it's 0 degrees outside. Heat pumps, on the other hand, they change with the outdoor temperature. The colder it is, the smaller the capacity of the heat pump. And I do realize there's new cold climate heat pumps on the market, extended capacity heat pumps, if you will, but they still respond to the outdoor temperature in interesting ways, and we need to take a look at their detailed capacities also. So this chart just sort of reinforces what I said before, is that here we have a furnace in orange, and we can see at 47 degrees, which is the orange color, it'll give you 64,000 BTUs. And sure enough, when it's 35, it gives you 64,000 BTUs. But a 5-ton heat pump at 47 degrees would probably give you something close to a 60K. At 35, you're honestly down, to almost a 3.5-ton unit. Let's look at a 2-ton unit over here. Sure enough, at 47 degrees, it's 24K. But by the time you get to 35, really you have a 1.5-ton machine. Heat pump goal. Heat pump goal in PTCS is to maximize the savings from heat pumps. In order to do this, we need correct sizing, a control strategy that minimizes the amount of strip or auxiliary heat, and a high efficiency heat pump. Keeping the strip heat off is the key to maximizing energy savings. Say a 3-ton heat pump is drawn about 3 kW and there's 15 kW worth of backup. Boy, as soon as that 15 kW backup comes on, you go from 3 kW all the way up to 18 kW. You basically increase the energy used by a factor of 6 when that happens. This is a detailed capacity from a manufacturer. Some of you might recognize the brand. This is interesting. It's a 2.5-ton unit, and at 47 degrees, their 2.5-ton unit gives you 28,000 BTUs. Not exactly a 2.5-ton, machine, but close to it. It's like a 2x4. It's a nominal value, and we should always look at the detailed capacity table. So this is the capacity of a single stage system, if you will. Down here on the bottom axis, we have the outdoor temperature ranging from 0 all the way up to 70. The capacity over here at the capacity per ton. So basically what we can see, sure enough, at 65 degrees, wow, we're above our full rated capacity. That's good news. By the time we get down to, say, 47 degrees, we're right at about 12,000 BTUs per rated ton, exactly where we'd be. And as we go down, we hit what's called the defrost knee, if you will, because at this temperature, you can make a lot of ice, and there's generally a dip in the capacity. But in general, the colder it is, the less capacity the heat pump has. Yes, we now have some extended capacity heat pumps whose curves look very different. Notice that the peak capacity on this system is at 27 degrees. It's actually higher there than it is when it's 52 degrees. Does this make sense? Yes, we don't need full capacity from the compressor at 52 degrees. It's much more likely that we'll need the full capacity at 27 degrees. And we can see that it dives off the colder it gets. Here's another system that's an extended capacity system. It's a little flatter. This one does have higher capacity at warmer temperatures, but notice this very flat spot here, roughly between 27 and 47. That's sort of where we live in the Northwest, so your capacity remains flat through that temperature range. Keeping the strip heat up, how do we do it? We size the compressor large enough to provide heat for the house all the way down to 30 degrees. 30 degrees is a balance point we like to see. It gives you a nice mix of capacity and a nice mix of efficiency and a nice happy homeowner that isn't freezing when it gets cold outside. In order to do this, we have to size correctly. And notice that we call the lockout strip heat at 35. That gives you sort of 5 degrees of flexibility, if you will. If you size for 30 and keep the strip heat off at 35, you'll avoid unwanted customer complaints. Definitions, let's just talk about balance point here a little more. It's the lowest outdoor temperature for which the output of the heat pump can heat the house by using the compressor only. Below this temperature, the strip heat might be needed to come on. So this is create, a heat pump balance point chart. The first thing that you do is you create the heat loss of this house. You need, 1 point to do that. You can take your heat loss at any given outdoor temperature. Usually it's your design temperature, and you anchor it over to 65 degrees. Sure enough, the warmer it is, the less the house needs for this to maintain temperature. So yeah, this house has a 45,000 BTUs at 9 degrees. Our first one here is a 2-ton, and if we just draw a straight line between the 17 and 47 degree AHRI rating points, you get a nice straight line. So the balance point where the two lines cross is 37. Not really a very good fit. The 3-ton gives you 33. We're getting closer. The 3-ton would give you 28. Nice fit. I think that'd be a very nice fit for this house. 4-ton, you're getting down to 25. And boy, you're probably paying lots for that, and chances are you'd probably also have to increase the size of the ductwork to handle that. Another way of looking at it, if you're going to use a 30-degree balance point, is what's the heat loss at 30 degrees? It turns out 30 degrees in Portland, Oregon is exactly the same temperature as 30 degrees in Bend, Oregon. So one thing you could do is you could just go into your software program and say, I'm going to override the design temperature. I'm just going to call it 30 degrees. That way you could just say it's 30 degrees, and I'm going to go into the detailed capacity tables and just see what their output is at 30 degrees. We see that the 5-ton gives you almost 40K. The heat loss is around 30K, so we could say that's oversized. The 4-ton gives you a nice fit. The 3-ton hits it perfectly. The 3.5-ton hits it perfectly. The 3-ton starts to fall short, 2.5, 2, and then just a little bit ridiculous, the 1.5 tons. So this is one way to think of balance point. You're just basically seeing what the heat loss is at 30 degrees. and then double checking what the capacity of the equipment is at 30 degrees and trying to get as close to each other as possible. So sometimes we hear, hey, how come you make such a big thing about the 30-degree balance point? Does it really make that big a difference? We look at Boise, and Boise is pretty similar to Bend, Oregon, for instance. And what we're looking at here is a Bend temperature chart. These are how many hours every year that the temperature is in a certain Bend. So between 40 and 44 degrees in Boise, we have 848 hours a year. So if you drop the balance point between 40 all the way down to 30, that's 1,553 hours, or the equivalency of 65 days that strip heat would have to come on to help heat the house. And boy, that's a lot of electricity to do. Let's take a look at Seattle. It's obviously more mild, but even in the mild Seattle, there's 930 hours between 30 and 40 degree F. That's equivalent to 39 days. So even in mild climates, getting a balance point of 30 is critical to energy savings and client satisfaction. Northwest heat pump sizing, we really get a break here. In humid summer climates and climates where cooling usage is high, Manual S dictates that the heat pump size not be more than 125% of the cooling load. The good news, when we get hot, we get dry. Manual J and Manual S, as they should be, are quite concerned about dehumidification in humid climates. When we get hot, we're not a humid climate. So if we stuck to this 125% advice we get out of Manual S, we'd often end up with tiny heat pumps that use lots of electricity. In most parts of the Northwest, 80% to 100% maybe on the coast of heat pumps energy is used to heat and not cool. So we're much more concerned about the efficiency in heating than we are in cooling. If you really want to dig into Manual S, the 1995 version says that if you live in a heating-dominated climate with dry summers, which is most of the Northwest, you get to use economic considerations, and that's really what the balance point of 30 degree does for us. Sort of gives us the best economics possible. Please notice that on the cooling design temperatures, they give you a few options. The 2%, that would be only 2% of the time does it get above 83 degrees. The 1% is 86. The 0.4 is 90. Well, summers are getting warmer and summers are getting smokier. The mean extreme is 99. I think that you would be fine, quite honestly, in climates such as Portland, Oregon, where there is a big gap between the average summer temperature and our mean extreme. I think you'd be fine using this 0.4 at 90, or maybe in some cases the mean extreme. But I would never use these 2% or 1%. Heating, you can go for the 99 or the 99.6. It's a difference of 5 degrees. I would not use the mean extreme for the heating in Portland, Oregon. This is the official summer climate map of America. Down in the southeast, if you're flowing down to Baton Rouge in the summertime, you probably walked off the airplane and immediately started sweating and could not wait till you hit your air-conditioned hotel room. It's really hot and it's really humid, and that humidity is the reason we call it air conditioning and not air cooling. Down in muggy places of our country, it is just as important to dehumidify the air as it is to cool. Air conditioners down in this part of the country have to be sized for both latent load, which is the ability to remove moisture from the airstream, and sensible load, which is the ability to cool the air down. Back in the Northeast, it's not quite so hot, but it can still be really humid back there. Our Southwest is just blazing really hot, but it can be dry as a bone. In the Rocky Mountain states, hot and really dry. And up here, we're sometimes hot, and when we do get hot, we get dry. So yeah, just going over the definitions of sensible and cooling load. The sensible is that part of the cooling load that involves lowering the dry bulb temperature. And dry bulb, this means a regular thermometer. If you put it in your house, you put it upside, that's the dry bulb temperature that you're getting. The latent load, that's the part of the cooling load that involves removing water vapor from the airstream. In muggy climates, this is critical. Before sort of Manual J and Manual S came out with such good guidance, we had contractors in hot, humid climates with customer complaints, and they'd simply put a bigger air conditioner in. The trouble with that is, yes, it cooled down the house, but rather than being hot and sweaty, you ended up cold and clammy, a condition that nobody likes. When you have a latent load, it reduces the ability of the air conditioner to lower the air temperature. Some psychrometric definitions. Dry bulb, that's the dry bulb temperature measured by an ordinary thermometer or thermostat. Wet bulb. Obviously, you have digital psychrometers these days. This is an old school way. I like these ones because I can understand them. You have a dry bulb, and then you have a wet bulb on this mercury thermostat. It's a cotton sock, and by the way, it has to be cotton, and a little water reservoir down here. So the cotton sock wicks up the water, and then you hold the main body and you walk around the room and you twirl this for a while. If it's really dry, you get a lot of evaporation off the cotton sock, which lowers the temperature of that mercury. If it's really muggy, you don't get so much evaporation. So when it's dry, you get a big difference between the dry bulb and the wet bulb. And when it's muggy, you don't get much difference at all. So all of us have probably heard that, hey, that air conditioner is getting us a 20-degree split. It's working just fine. And, you know, for large parts of the year in the Northwest climate, that's true. Say we have an indoor dry bulb going into the coil, the indoor coil at 76, and the indoor wet bulb is 62. Yep, guess what? You have the ideal temperature split. But just to say you get out there, and it's early in the day, the system hasn't been running to dry out the air. It's a little muggy. Let's just say you got a 68-degree wet bulb, which is pretty wet, and the same 70, let's say a 78. Well, then your expected temperature drop across the coil will be 17. Let's say you had a 72 degrees indoor dry bulb temperature, then you'd only be expecting a temperature drop of 14. So while the 20 degrees generally works for us in the Northwest, it's still nice to know something about the psychrometric conditions you're testing under. What Manual S says about cooling, don't oversize by more than 115%. That's hard, no more than 125% if it's a heat pump. Why are they so worried about this? Is because they're worried about dehumidification. The good news is that we don't have to worry about dehumidification in the summertime in the Northwest. If that air conditioner is running at all because it's hot, it will provide sufficient levels of dehumidification. Also, older air conditioners had a big penalty for not having long cycles. Newer equipment has improved significantly. What the penalty for cycling is something called the C sub D, or the coefficient of degradation. It's used to describe how the efficiency of air conditioner heat pump is degraded by cycling. It used to be C sub Ds would hit you up with maybe, you know, a 25 or 30% penalty if it's cycled. The new ones are much lower than that. A good estimate that oversizing an air conditioner in the summer by a ton might only get you a penalty of 40 degrees on energy efficiency. I'm not advocating oversizing. Again, you know, just hit this up. Manual S says don't oversize. Why? Because they are quite concerned about dehumidification. Sizing for air conditioners. Every manufacturer presents their detailed capacity just a little bit different than every other manufacturer, making our lives sort of complicated. But regardless, the process is usually the same. You find the outdoor design temperature. In this case, it's up here near the top. You determine your CFM, and this happens to be for a 2-ton system. You start at 800, you go to 900, you go to 1,000. Please notice it doesn't go down to 700 or 600. So again, these charts are only valid that if you have perfect airflow and perfect charge. You pick the lowest entering wet bulb. 62 or 57 degrees is safe. Remember, it's going to be hot. The air conditioner is going to be running for a long time, and the air will get dried out the longer that air conditioner runs out. And then you locate the sensible capacity. And this manufacturer showed basically sensible capacity in a different table. So please notice here at 72 degrees entering wet bulb, the sensible capacity is only 13,000 BTUs per hour. The total capacity is 26,000 BTUs per hour. The difference is all tied up in latent capacity, in removing and turning that humid, muggy air in form of vapor into water. Boy, at a 62 degree entering wet bulb, it's almost identical. By the time you get down to 57, it is identical, meaning the capacity of that machine is all sensible and it's available to lower the temperature of the air as it goes through the coil. This is another way of looking at it. Again, we're going to find outside temperature. Here, the axis is here. This is, say we're going to pick on 95 degrees today. Determine your CFM. Notice that they don't give you any CFM. It tells you it's fixed at 1200. You fix the lowest entering wet bulb. We're going to use 59 degrees. Locate the sensible capacity. Well, here they give you the total, which is 32, and they give you the sensible capacity, which is 29. So this is a 3-ton machine, and they're telling you that underneath these conditions, the sensible capacity is 30,000 BTUs. It's not 36,000 BTUs. And if for whatever reason you wanted to go to a humid climate, say it's all the way up to 67, your sensible capacity would be actually less than a 2-ton machine, roughly at 21,000 BTUs. A little word about geothermal. At least one person in your company needs to be ICSPA certified. We'd like to see a balance point of 25 degrees or lower. And here's the important part, is when you're doing the calculations, the balance point must be calculated in incoming water temperature of 30 and not 50. There's a reason we put antifreeze in the loop, because it does get cold and might freeze. And by the end of winter, in most systems we've inspected, the incoming water is close to freezing, not below freezing. Manual S, when it comes to selecting these things, understand that latent and sensible cooling loads are two separate items, and you have to meet each to obtain comfort. In cooling mode, the good news is our latent load is really tiny. Just to show you just how this works, infiltration accounts for most of the latent loads. In humid climates, leaky homes let that moisture in. In dry climates, it's so dry outside that the leaky homes tend to have lower latent loads. Sizing for cooling, most parts of the West, it's easy to handle the dehumidification. Air conditioning, originally meant two things, dehumidification and lowering the sensible temperature. Other key part is how much insulation's in that house. What are the windows like? What are the ducts like? Those are the critical elements. And, I'm old enough to know that, old enough to remember that when we used to do this, we had big 3-ring binders that we got every year. And we had to, carefully look up the new equipment output tables and looked at carefully. Now everything is online. But basically the process here is, do accurate heat loss, heat gain. One thing I would like to stress here is that a lot of programs for their default window U values, especially in the Northwest, we have a long history of codes requiring U values for windows of 0.4 or less. And some programs, if you say you have a double pane vinyl window, they'll assume a U value of 0.5 and a fairly high solar heat gain coefficient. In the Northwest, almost all our vinyl windows are 0.40 or better. Any new home will have a 0.35 or better. So double check the default U values of whatever computer program you may be using. This is what the detail stuff. Insulation, none, some, fair amount, or a heck of a lot is usually sort of close enough. House tightness, this is another error we see a lot. ACH, the leakage rate of the house, air changes per hour, is usually between 0.35 and 0.8. It's never 2. I have seen heat loss and heat gain calculations at 2. That's a barn with the door open on a windy day. When the solar heat gain coefficient is critical, you can usually find that generally in the northwest it marches right along with the U value. So if you have a 0.35 U value window, chances are solar heat gain coefficient is very similar. Orientation is critical. Windows that face east and west get most of the summer sun. It's low in the sky and it can just beat through it. So make sure you have the windows in the house pointed the right direction. Duct multiplier is critical. Boy, 15 to 20% is really a pretty good estimate. I know many of you don't do duct leakage tests, and that's perfectly okay, but I urge you to do what I at least call the Homer-Simpson duct leakage test. That's where you turn the system on, let it run for a while, so you're either heating or cooling, and go around to each register. And is there conditioned air coming out of each register? If not, go find out why. It might be a disconnect or it could be a closed damper. House size is important, but not as important as insulation levels and window U values and window orientation. You need to know the capacity of the heat pump at your desired balance point. You can either do that by direct lookup or drawing the traditional balance point diagram. And also, don't forget to pick the right location. Remember where you live.